G'day, everyone. Today we've got a really, really exciting interview. So with me today is Dr. Juan Flores Preciado. He's the lead of the surface engineering group actually at SpaceX. I'm super excited about this interview because I actually came from an aerospace engineering background myself, but have never actually worked in the industry. So always had a lot of interest and been keeping tabs on all the kind of the huge developments that have been going on, especially over the last, let's say, 6 years. So really excited to get into it, but I'll let Dr. Juan sort of introduce himself and his background and how he really got into the space industry as well. So if you could please take it away.
Yeah, definitely. Well, thank you very much for the invitation. This is actually a very good channel for us in the tribology industry. Of working, in the industry as a tribology engineer or a surface engineer in my case, I think it's a very good opportunity for us to show what we do from kids all the way to people with like 20, 30, 40 years of experience. As you mentioned, I'm currently working at SpaceX. I'm the lead of the surface engineering group. It's a relatively newly created group, and we basically work on areas related to protection of surfaces, right? Protections against harsh environments such as corrosion, protection against friction, wear. Therefore, tribology plays a very important role. This is a relatively new area for us, especially now that we are sending satellites or, we're sending a spacecraft that spend more than a few hours in space.
Yeah.
So longevity now is more important for us. And also, we do everything that is related to, the surfaces of different components. So that's what my team is currently doing. Uh, I was never an aerospace engineer. I was never one of these guys that really wanted to build rockets. I guess when I was a kid, I always wanted to be in the car industry. But then I realized that I was really bad designing things. I don't have imagination. You see how empty is my wall? There is really nothing there. And I said, all the fancy things that you have over there. I started working after my PhD. I did my PhD in England in a very strong tribology group in the University of Leeds. And then after that, I started working for General Electric in the research centers of General Electric. Right then, I was also working a lot of surface engineering stuff, but more related to harsh environment, like radiation damage for nuclear materials, heavy corrosion and stuff like that. And then after 4 years in upstate New York and a lot of snow, I realized that the weather wasn't for me. So I moved to California to work for Caterpillar Energy. And the same thing, I was also working on surface engineering, mostly for protection of components at very, very high temperature. So all the lubrication that I was using at the time was high temperature, right? So petroleum-based lubricants, we were not able to use them, at least not for the power generation. Obviously, Caterpillar uses a lot of greases and oils and stuff like that, but no for the gas turbines. And then after a few years there, I joined SpaceX, and I've been there for 3.5 years now. So far,
Oh, wow. Wow. That's,
yeah.
that's, that's amazing. And one of the cool things I've experienced, with this channel is, whether in this interview format or sort of outside of it is being able to talk to people who seem just have like, really good experience and in some ways are just in like absolute dream jobs at the moment. Just one thing I guess I wanted to backtrack on a little bit because some people might be a little bit surprised is, I
Mhm,
guess when you said when you were working with GE, you mentioned,
mhm.
the potential for radiation damage,
Yeah, yeah,
materials and lubricants. So I'm guessing you were
right.
working in sort of like the nuclear power industry.
Yeah. So then I was working for GE. So I was working in the General Electric Research Center. So GE is so big that it has a research center for all the different GE businesses. And my work was mostly sponsored by GE Nuclear. So it was mostly about what is the effect of all the radiation neutrons and what have you on the structural materials and also the different lubricants that are used there. Uh, and believe it or not, because radiation is something that you also see in space,
Yes.
understanding the effect of neutrons on materials uh, provide a good foundation for me to understand the effect of gamma rays, so atomic oxygen in space. So same physics, yeah, different energies. So
Yeah, yeah.
yeah,
Yeah,
and
I guess I just wanted to highlight that because for, for anyone who's comes from a country that, doesn't have nuclear power, it's not
mhm,
necessarily an application that sort of,
right,
immediately jumps out at
right,
people, right? But
right.
like you said, it sort of translates really well to the space environment.
It
I was
does.
wondering if maybe just to start off with, we could talk about the environments required, in space travel, um,
Yeah.
and how it's very different from Earth. So maybe to sort of preface the question, I think the space industry is such an interesting one because you have to cater to multiple environments, right? So, you have to be able to um, provide protection from a tribology standpoint on the ground
Yeah.
during launch phase, which is very
Yeah.
different to low Earth orbit, which is very different to deep space, which is very different to reentry.
Mhm.
So
Yeah.
maybe if we could describe a few of the challenges of those environments and what's a little bit unique about it.
Right. So I would like to say, like, for instance, as you say, right, when you are in ground on ground, right, let's say from wherever you have your space station or your launch site, uh, it's very important to protect things against corrosion as well, right?
Mm.
We do not have a lot of systems that rotate, at 100,000 RPMs and stuff like that. We have a lot of systems that they have to withstand very heavy loads. Uh, we have a lot of systems that maybe have to rotate a little bit like antennas and stuff like that, but the rotation speed is definitely not very fast. Uh, but we have a lot of components that will require some lubrication and also some corrosion protection at the same time. Many times, the systems that need lubrication are usually exposed to the environment. They are not in cages or encapsulated or protected from the environment. So that's a couple of things. And also, some of the systems that are located close to the launch pad may be exposed to high temperature. So it's very important for us to take that into consideration. So we don't use a lubricant that may not be able to withstand those temperatures, or a lubricant that may suffer degradation because of the contact with sodium chloride or sulfates or other kind of chemicals in the environment. For the grand majority of machines, my team doesn't usually work on that area. Uh, we have more like a maintenance team that does all the, maintenance and protection of those systems. For systems that are a little bit more complex, then we can probably help them with that as well. Uh, and then for the rocket, obviously, a section of the rocket doesn't really stay for a very long time in space. We just go there, release our load, and then, we land there. So the same thing, in that case, uh, it's almost like an airplane, in terms of like the type of protection that we need to provide. Yeah. And then once you are in space, then you have to take many things into consideration. Like the environment there is no gravity, right? So there is no way to put oil down or, to specific locations for liquid lubricants. And also the lack of oxygen, right? Many times for some of the greases or lubricants, you need some gases or moisture, something like that to form this famous tribal film or to form an oxidation or, an oxide layer on the surface. So there is no such a thing. Yeah. And also we have a couple of radiation issues in the space. You have UV, uh, not the regular UV that you see here, right? But UV without the protection of our atmosphere. Uh, and UV can be considered a type of radiation as well, right? That may interact with the molecules of your oil. And then, basically, the impact energy is so high that it's just going to pull apart some of the carbons in your chain. Yeah, so those are some of the things that you have to consider, basically, the environment. Uh, and in our case, we have basically three different environments, and then all the way to like vacuum of the space with, many is you don't provide oxygen, is you don't provide moisture, and is a zero gravity. The number of products that you can use is like reduced to like
Yeah.
just a few.
Yeah. One thing I wanted to sort of maybe ask you about, because you touched on it there, was, you talked about the low oxygen environment.
Right.
The way
Yeah.
I understand space environments is that there is both too little and too much oxygen. in the
Yeah.
sense that, when you're in low Earth orbit, as an example, where a lot of satellites might sit, um, communication satellites and things like that, um, the type of oxygen that's up there is atomic oxygen rather than
Correct. Yeah.
molecular oxygen.
Right.
So for anyone who's not familiar, oxygen obviously comes as O2, right? We
Mhm.
breathe it in, but when you're in low Earth orbit, generally there's enough radiation that it's broken
Yeah.
that oxygen apart, and so oxygen
Right.
exists as like a free radical, effectively, right? And
Exactly.
because
Yeah.
it's so
And you know,
reactive, it's looking for
right.
something to sort of grab onto,
Yeah.
and so
Yeah.
that can accelerate,
Mhm.
the oxidative breakdown of most materials.
Mhm.
So, you know, are there specific ways that we can kind of, I guess, design uh, materials and, um, you know, lubricating greases and oils to deal with that?
Yeah. So there are a few efforts and there are a few lubricants that can be used, especially in low air environment. Like for instance, the International Space Stations use some lubricants that have fluor, that have, instead of the regular carbon, hydrogens, it has some other molecules.
Yep.
Uh, the Basically the bonding strength is significantly greater than the bonding strength of a carbon and a hydrogen, right? Which are just hydrocarbons, right?
Yeah.
But when you have all these extremely difficult to pronounce, PTFEs and the PCPEs and what have you. One of the reasons why I didn't study organic chemistry, uh, you know, the bonding strength between these two molecules or these two atoms is significantly greater. So the energy impacted by the atomic oxygen, it's just not strong enough to uh, to remove those and to significantly affect the integrity of the molecular structure of these lubricants.
Okay.
And that's why many times silicon-based lubricants work well, fluorinated lubricants work well in terms of withstanding the atomic oxygen. There is a nice video. I don't remember the name of the astronauts where they basically have an issue with the solar panels in the International Space Station. They rotate really slow, right? They just basically like a sunflower. They just have to follow the sun. So they don't rotate really fast. But they notice an issue with the torque that was required to rotate those panels. And they realized that it was a lack of lubrication. Uh, because they use like a hard facing material. So back in the day, they used to use gold or silver. Uh, and then what they did is, they send back in the days when they have the Atlantis, I think it was Atlantis, and they were able to apply one of these fluorinated greases uh, in order to reduce the friction and therefore to, go back to the normal torque that was required to rotate those. Yeah.
Yeah. Okay. And so I guess so for PFPE compounds, we actually did a video on this channel about a month.
Oh, okay.
If anyone wants
That's
to
it.
go back and take a look at that,
Yeah. I will.
there'll be a picture of like what PFPE compounds sort of roughly
Yeah.
look like. I mean, I didn't go into
Mhm.
it in any kind of detail. It was probably only 10 minutes or
Mhm.
something like that. But um,
Mhm.
I guess one of the advantages I understand of that product as well is it has extremely low volatility.
It does.
Right.
Yeah.
And one of the
Yep.
problems that you have in space is you get high
Mhm.
temperature extremes that are going to volatilize off really any hydrocarbon, right?
Yeah. Yeah.
So,
Yeah.
yeah, so I guess that's one of the other advantages. Maybe just
And also no vapor pressure.
yes, yes,
So they can withstand high vacuums. Yeah.
yeah.
Right.
One of the I think maybe one of the ways that we could go through this is to sort of talk about the three uh, main, let's say, types of lubricants that are used. So you've got liquid and then grease and then solid lubricants. So maybe first starting with liquid lubricants, because I know there's um, maybe the window of applicability is quite a bit smaller in space applications because of things like,
Mhm.
you have to deal with the vapor pressure. Um,
Mhm.
how does, let's say, for example, our understanding of building a hydrodynamic film in Earth applications is that, I have a bearing and it's rotating. And, you always think of the liquid lubricant sitting, on the underside of the bearing.
Mhm.
And as the bearing picks up speed, it sort of develops that film. Now,
Yeah.
in a zero gravity environment, you can't put the lubricant where you want. So how does bearing
Yeah.
lubrication or any kind of liquid lubrication, how does that work in space?
Yeah. Yeah. So yeah, you're right. As far as I know, at least at the moment, we don't really use any liquid lubricants in any of our systems. We probably use some on the first stage rocket, mostly for cooling, but many times we use fuel for cooling.
Mm.
We use air for cooling. We use hydrostatic bearings, right, to provide that initial film, especially for our engines. Or we use, I mean, solid lubricant. But to answer your question for
Yep.
liquid lubrication, no that I'm aware of, not at least for our, current applications. Yeah.
Cool. So then if we move on to sort of greased
hmm
applications,
hmm
so I know that gets pretty exotic too, right? Because let's
Yeah.
say, for example, with some of the greases, um, some of them, the way that I understand it, are PFP base oils
Yeah.
with like a PTFE type thickener.
Correct. Correct. Yeah.
And that would mean, I don't know what kind of companies you guys would work with to make
Yeah.
products, but the way I also understand it is that because PFPE base oils are so different from standard hydrocarbons, it also means that there are basically no additives that we can pull across from our standard hydrocarbon greases to use, which means it's an
Right.
entirely different additive chemistry set as well.
Right. 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 Yeah.
So,
Indeed. Actually, yeah, you're right. Yeah. Go ahead, please. Sorry.
oh, sorry, I was going to ask maybe two questions. Are you working with let's say like standard grease companies who just produce these in small volumes, um, specialty greases? And then the next question would be about application of greases in a space environment as well.
Yeah. So the company, we don't really work with a specific oil company, risk company at the moment for developments. I think there is enough. I don't want to say a significant number of products available in the market, but the fact that you have NASA, you have the European Space Agency, you have JAXA, so there are some products available in the market. And as you
Yeah.
say, the majority of the time, the additives that are used are either to improve creep resistance of some of the greases or improve the loading capability of some of the greases as well. Uh, and or sometimes even temperature capabilities, right? But the majority of the time, you still use inorganic additives, right? You are using either molybdenum sulfide in the greases, you are using calcium fluoride, maybe you want to increase a little bit the temperature capabilities, uh, yeah. Or, some other kind of inorganic additives is you want to is you want to reduce polymerization or you want to increase the contact loading capabilities. Even castor oils, I think they have a number of products that are used for space. And that's very interesting, right? Because many times the companies put a lot of money on space applications and then they realize, oh, I can also use it for like ultra high vacuum machines here there, right? And then you have a lot of systems like physical vapor deposition, chemical vapor deposition that require this kind of like, high vacuum lubrication systems. And, there is a market there. A lot of people always ask like, why do we put so much money in space? But many times some of the space products can be used on, terrestrial applications as
Yeah.
well. Yeah.
Yeah. It's
Yeah.
yeah, you're right. I mean, effectively, what the space industry is doing is sort of pushing the envelope of performance
Right.
because you have to
Exactly.
deal with such extreme, temperatures and pressures and all the rest of it. And yeah,
Right.
the technology that's developed always eventually filters its way down. Sometimes in
It does.
not very obvious ways, right?
Yeah.
Um,
Yeah.
okay, so that's sort of greases. So that helped me understand a little bit because I was wondering whether it's everything has to be specifically developed or whether there are actually off the shelf products for the space
Mhm.
industry. Um, and then the next question would be around application because similar thing, you're in a zero gravity environment. Now, fortunately, you're probably not having to deal with some of the complaints that the industrial guys will have about, water washout and sprayed out and things like that. But I guess the other thing that you've got to think about as well is that basically every application is fill for life too, right?
Yeah. Yeah.
It's not like you get to go up there and re-grease a bearing
Right.
all
Exactly.
that often.
Yeah.
Um,
Yeah.
so, and I'm thinking even about some of the, um, deep space missions that have already been run, Voyager and that kind of stuff. I mean, some of those applications have been out there for 20, 25 years,
Yeah.
even longer, right? And they're still functioning. So,
Right. Right.
so yeah, just with regards to grease application, um, is it generally just, fill for life bearings that they're all packed in and we just don't touch them? Is there any amount of grease application that happens?
Usually for greases, you want to keep it as thin as possible. And something that we have learned in the industry, and especially again from NASA reports or ESA report, you have to apply your grease heat in air, do all the testing that you have to do, and you will realize, it's performing really, really well. Uh, but some of the lesson learned, especially from Galileo and some other missions, is like, before you send it to space, you may want to reapply it again. You may want to replenish those greases because we do so much testing sometime here and there, right? We cannot afford to lose a vehicle. We cannot afford to lose a satellite. It's a lot of money there. So we tend to do a lot of testing. Uh, and then it is very important to be sure that you also replenish the lubricant before the actual mission. One of the issues that we notice when you apply too much grease is it's a foot magnet, attracts a lot of like just dirt or debris or stuff like that, right? So it's very and if you apply something that's relatively thick, there is more the possibility to attract more of these debris or fall just flying around is even greater. So that's one of the issues that you have to keep in mind about greases, right? Is you have to apply a grease or a mechanism or a device. Just want to be sure that it's in a relatively clean environment, in a clean room, that is just enough amount of material. Yeah. And believe it or not, we don't really have a specific tool to ensure that you apply a super thin layer because of the viscosity and all that, right? It's just, best practices and definitely do some wet film kind of like thickness analysis. But yeah, in terms of space, it has to definitely be a very thin layer
Yeah.
of the greases that you apply.
Yeah. Okay. Really interesting. And then maybe the third area of let's say lubricant type is obviously the solid lubricants,
Right.
which, the way I understand it, very well suited for space environments, probably more so than on Earth, because again, if you've applied it as a surface coating, then you don't have to worry about zero-G environments. My understanding of molybdenum disulfide or some of its variations is that they actually perform much better in low oxygen environments.
They do.
As well.
They do. Yeah.
So, maybe could you please describe a little bit about sort of the history and the development of some of these solid lubricants, even the way that they're applied, because that's very different in space technology.
Yeah, definitely. Yeah. So as you say, something that I think is going to be the future, or part of the future of the space a lubrication is solid lubricants. Actually, we're actually working with Professor Martini from the University of California, Merced, because it's literally just driving distance from where we work.
Yeah.
And I definitely believe that solid lubrication is a very important area of R&D and area of expertise. So basically what you have is materials that have a very low, extremely low shear strength, right? It's basically like when you're writing with your pencil, right?
Yeah.
You see how easy it is to like basically shear the graphite from your pencil. And that is because it has very low shear strength, right? But you have to continue to use the mechanical sharpener, right? Because, the wear life is relatively short, but it's predictable. You can run an easy test and you can predict the wear life of that solid lubrication. So that's the magic of solid lubricants, that is very low shear strength. So you don't really need to apply a lot of, shear to just basically have this kind of lubricity from these lubricants. So that there are widely used is molybdenum sulfide for sure. Tungsten sulfide is also widely used as well, although that one doesn't have as good as corrosion protection as molybdenum sulfide. And if you want to go a little bit higher temperature application, you can use graphite. If you want to go even higher application, then you can use boron nitride as well. And then, a lot of different compounds in between as well that can be used, calcium fluoride, etc. And it's basically the same principle, right? The fact that they have a very low shear strength. And then you just have to be sure about the selection is based on what is the effect of the environment, right? As you mentioned before, molybdenum sulfide has a negative, moisture has a negative effect on molybdenum sulfide because it can react with the molecules, right? And reinforce or increase the shear strength of the molybdenum sulfide, right? Therefore, it's going to be a little bit harder to obtain this lubricity. You need greater loads, and therefore your coefficient of friction is just going to be higher, right? Because the bonding is significantly stronger than just a regular molybdenum sulfide. And that doesn't happen in vacuum, right? In vacuum, it's nothing but the interaction of the molybdenum sulfide, planar structure. There is no oxygen in between or hydrogens in between reinforcing that. Graphite have an issue sometimes because sometime in space, it doesn't have as that's very good vapor pressure, and also graphite needs oxygen. It needs to form a tribal film with environmental gases or with hydrogen from water. There are some papers that do a lot of atomistic R&D, atomic force microscope to really understand what's going on between the carbon, because graphite is nothing but carbon, whereas molybdenum sulfide is an actual molecule.
Yeah.
So carbon needs like a passive layer to have a better wear rates and a lower coefficient of friction. That's why if you test on a pin on this system, graphite in a dry environment, you may have a COF of 0.4. And if you add a little bit of water or increase the humidity of the room, you may have a coefficient of friction of 0.2 because you are helping that tribal film by adding a reactive gas or by adding humidity to graphite. And one of the issues with graphite is sometimes the debris may be conductive, and that may be detrimental for equipment in space. So that's why we want to avoid the use of graphite. Some of the components.
So conductivity is sometimes desirable, right? So
Sometimes
like
it is.
in a slip ring application, for example, where you actually want to transmit an electrical signal between basically a stationary and a rotating object. So is that an instance where you would use a graphite compound?
Yes, exactly. Yeah. And something that is very important about solid lubricants, because the solid lubricant is a particle, so the compound, right? You have molybdenum sulfide powder, and then you have graphite powder, and then you have boron nitride powder. But then you have to find a way to apply that powder into a film.
Yeah.
Right. So that is also another kind of area of research. Like now I'm bringing my PhD back to the conversation, I guess, where people use different binders, right, to glue those particles together and create a coating, right? And then even the selection of the binder, in order to do the best selection of binder, you have to understand the atmosphere, right? Yeah. You can use epoxy binders, you can use polyamide, you can use petroleum-based binders, similar to the binder that you use for your house paint, right? But then if you want to withstand higher temperature, then you can use silicates binder, right? Silicates is like basically minerals that you use in combination with water to create what we call liquid glasses, right? You basically create a glass based on potassium, lithium, and silicates in general. That will increase the temperature capabilities of because it's no longer an organic binder, it's an inorganic binder. And there are other options such as physical vapor deposition. That is a more fancy vacuum erosion, basically eroding tablet made of molybdenum disulfide under a very high vacuum condition. And that's another way to apply this coating, right? So again, one thing is to have the powder, but then you have to apply it.
Yeah.
And then, you have to find a way to do it. And that's when the application of the solid lubricants, play a very important role. It can be applied as a paint, because you have an epoxy binder and then you just spray it. It can be deep. And also, it can also be rolled if you don't care about the thickness of the coating. But obviously, if thickness is very important for you, then you have to take into consideration the particle size. You have to use a more controlled way to apply it, such as, just a nice paint gun, and so on, right? And also sometimes you have to heat cure it if you want to make it more robust, right?
Mm.
Many times you can just apply it and let it cure, but there are some binders that will require some heat in order to basically cure the binder. So that's why I think the solid lubrication is a very important area, because there are so many boxes that you have to check before, they're ready to fly.
Yeah. That's so interesting. And I guess maybe there is actually a fourth kind of type of lubricant in some ways
Yeah.
related to solid, but self-lubricating components as well, right? So if I had let's say a bushing or a bearing made out of PTFE,
Yeah.
then Teflon, then effectively that you don't really have to do anything to that, right? That you just
No,
you install it
you're gonna let it roll.
and let it roll.
Yeah. Yeah.
Yeah, right. So
And there is another one, I guess, that is they are also considered solid lubricants, right? But they are like the diamond like carbons, like, all these nanometers or micrometer thicknesses of thin films, right? That are also and actually widely used right now on like long-term space missions, because their durability and because even though sometimes they offer a higher coefficient of friction, so the lubricity is not that perfect, but it's very uniform, it's highly predictable, and it's going to last for a very long time, right? So sometimes is you give the designers, hey, I can give you a coefficient of friction of 0.4, but it's going to be like that from here all the way to Pluto. Then they can probably, just recalculate the forces that they need to apply to move a mechanism, because of the peace of mind that this is going to last all the way until the end of the mission.
yeah.
Yeah.
And that speaks a little bit to, I guess, testing as well and prediction of performance. So I guess where you work at SpaceX, this will become sort of more and more important as the SpaceX starts to do deeper space missions, right? Like you pointed out, up until this point, it's mostly been, putting satellites into orbit, low Earth orbit missions and things like that. So I know there's a lot of experience, let's say out of NASA with, Hubble, right? International Space Station, applications that have been out there for a very long time, as well as some of the deep space satellites. How do you predict performance when the space environment is so different to where we could typically test materials here on Earth?
Yeah, you're right. So at this very moment, we are currently doing that, right? Trying to try to build our tribology lab and, acquire machines and systems to better predict, especially now that probably sooner rather than later, we're going to start doing like the long-term missions. So at the moment, what we're trying to do is collaborations, right? Is you need to run something at ultra high vacuum, then probably we can do a collaboration with a university. Because you are right. If you want to properly predict the web life of whatever mechanism, your environment has to be as close as possible to the actual and the real environment, right? It's like, for instance, is there is someone asking me, hey, I want to design this system. I just need a coefficient of friction of 0.3, and then I need a bit of corrosion resistance. I'm like, oh yeah, I can totally do that. I can give you a solution very rapidly. And then, but also it has to have an extremely good impact resistance as well, because everyone during the mission, you're going to have some vibration. And you're like, oh, okay, then it's now more narrow, right? Oh, and it's also have to, you also have to be able to code this gigantic mechanism, I'll say, okay, so I can no longer use a PVD system because, there is no such a large chamber. And then you also have to withstand cryogenic temperatures and also maybe all the way to 200 degrees C. So then, yeah, you're right. You have to fully understand your environment. And you can do two things. Number one is just test for the most extreme environment, maybe just test temperature and use a coding or a system with enough history that is proven that it's going to behave okay at the high vacuum conditions, right? And then you don't need to test that because there is enough, literature to see, what material, what coating, what lubricant is going to behave under high vacuum conditions. So sometimes that's basically what we do. We have to compromise, maybe we cannot test this, but I'm using a material that, have enough information or enough data that I think is going to withstand, this or that environment.
Yeah. And it's so interesting because, in the industrial world, we have an opportunity to do used oil analysis, right?
Yeah.
Which in many respects is a way to validate your original assumptions about oil life.
Yeah.
We're continuously testing, gaining more data, and that can feed back into your models. Obviously in space, you don't really have an opportunity to go up and take an oil sample.
No.
The way I understand it is that there have been a handful of times, I think one time on Hubble, where they replaced one of the reaction wheels or something like that, and they brought it back down and were able to do a grease tear apart to sort of validate the model. But those data points are few and far between, right?
Yeah, they are. Yeah, they are. But the good thing about that is because many of those missions are government missions. Many times they have to publish the data. So that's another thing with tribology. Tribology is a very expensive discipline. Testing is expensive. So many companies, they just don't share the data, right? I don't blame them. You have to spend a lot of money. But so for some industries, such as the space industry, that still has a lot of government support. Most of these researches are publicly available. So sometimes it's definitely there. And also sometimes what we do is like, we not only use one solution, right? We don't only use a lubricant. We may also use a hard coating in case that if the lubricant fail, then you use a hard coating at least to avoid galling, right? So there is always A, B, C, and D, right? So that's why many times space mechanisms are definitely simplified, like over designed, right? Because you cannot just go there and change the oil. Right. So therefore you have, different levels of protection.
Yeah. But even that is
to provide the best one.
Yeah. Oops, I've frozen. But even that is, I was going to say, a bit of a trade-off as well, because, in a space environment, you can't continue to add weight.
Yeah, correct.
Right?
Exactly.
So there's only so much redundancy that you can build into your application, without, sacrificing, mission payload and all that kind of thing. I think one of the other things which would be really interesting to talk about is actually the different applications on spacecraft too, because some of the mechanisms that you guys use in the space industry are a bit different. So it's not like people are familiar in the industrial world with a lot of internal combustion engines, which, there are obviously rockets, right, attached, but not internal combustion engines in the way that we would talk about your car or a truck, right? Not reciprocating engines. And then, of course, there's going to be a handful of pumps and electric motors. I think one of the more interesting lubrication points that I've seen is reaction wheels. So the gyroscopes, which are trying to basically orient satellites without having to, give up liquid propellant, right?
Right.
For want of a better word. So maybe if we can talk about some of those, because some of those applications are familiar to us from, let's say, the Earth-based world, but have to operate in much higher extremes. So the one that sort of stands out for me is let's say, for example, in electric motors, we have some electric motors here on Earth that, yeah, they have to operate in relatively extreme environments. But electric motors in space applications, let's say, for example, I have to guarantee the performance of the electric motor on re-entry, right? When stuff is literally so hot that, the gases in front of, uh, in front of the spacecraft are ionizing.
Yeah, it's a
Um,
plasma.
yeah, it's plasma. Um, it's like, again, first of all, how do you test for those like real extremes? Um, and second, is it all about just building in redundancy, or what are some of what's a little bit different about, I guess, the
Mhm,
space landscape?
mhm, mhm. Yeah, so I guess that a more like genetic, from a more generic point of view, yeah. So we do definitely a lot of testing.
Yep.
Um, we do have another testing rig, some kind of micro subscale testing applications, but also we use a lot of metallurgical aspects of the materials, right? Material that can definitely withstand the higher temperature, and therefore, just because the material itself, is able to withstand all these, conditions, there is no additional, protection is required. Or maybe there is some thermal protection that may be required. And then you just use material with a lower thermal conductivity, for instance, right? To delay, you know, reduce or eliminate the amount of heat that is being transferred from the exterior uh, to the interior or to the machinery and stuff like that. So yeah, definitely they use a more like, I don't want to say fancy, but more like high alloys materials that can withstand. Those are the areas where probably we can add more weight,
Mm.
right? In order to ensure, full protection of the different devices and components. For the rotating wheels and all the gyroscope that we use in the satellites, we do not manufacture those ourselves. These are coming, I think, from another company. Not 100% sure, but yeah. But all of these mechanisms in the space that need to rotate at very high velocities, very high speeds, and they need a excellent level of precision, right? Normally use some kind of either hard coating, thin films, or dry lubrication. If you use liquid lubrication, and for whatever reason, there are some areas with a little bit more oil than other area, that is going to unbalance, right? The entire satellite. And the satellite is going to be, okay, I think I need to go lower or I need to go higher because, I'm biased towards like one side or the other because of, liquids under vacuum condition. Again, it's very hard to pump. So instead of like, having a pump, pumping this liquids or pumping these lubricants, you just save that weight. And, for using a material that is probably a little heavier, but it can withstand, temperature or radiation. Uh, and nowadays, definitely the use of thin films is like, it's just pretty much everywhere. It's widely used. Mhm. Yeah.
Yeah. That's so interesting. Um, cool. Well, Dr. Flores, thank you so much. I think,
Thank you.
I learnt so much, and it's such a cool and interesting field. Not only because the application is so extreme, but just
Yeah.
because of all the activity that's going on in the space industry at the moment. It's really exciting place to be, and
Yeah.
yeah, wish you and obviously the rest of the SpaceX team all the best of luck with future missions.
Thank you very much, and thanks for the invitation. And yeah, I'm happy to be getting. I think you're doing a definitely good job, bringing tribology, to this planet. And hopefully, there is a new tribology engineer, listening and watching this video.
All right, thank you.
Thank you. Have a good one.